Up to this point in this course, we've been studying what I call passive nodes in the finite element analysis. Now I'd like to change direction and consider what would happen if there were a control system that introduced forces at these nodes. And these forces are not just external, but they are internal, and they intervene between the degrees of freedom, say on a left-handed element and a right-handed element that join at a common node. This is a new idea and something I'll have to explain in more detail when the time comes. So we'll look at active nodes, and then I'll take a specific system. We'll look at a Flyswatter, a robotic Flyswatter, and then I'll go through 3 problems in a problem session. Let me review the common usage of our nodes in the past, and then we'll gradually work toward the active node. In this figure, I have 2 usages that we have already encountered. The most common one is when the node is considered to be welded, and then it's pretty easy for people to appreciate that under load that this body would follow some smooth curve. They don't expect to see a kink develop at either of those nodal points. Interestingly, if you go to the next more difficult step, namely a cantilever beam which has a kink in it at the outset, and then you put a load on that, there are many people who, for some strange reason, might expect that this joint here would then develop a different angle than the one shown currently. Currently I'm showing about 160 degrees there, and so if I drew an included angle here of 160 degrees, and you ask students would that open up upon application of the load, they would say sure, it might be 170. Wrong. That angle cannot open. It's a weld, and you can't get any accumulation of a finite change in angle at a point. Well, maybe that's a little bit of a difficult concept, but people usually follow that. I know that on my hollow octagonal electric pole arm, that when I asked the students to make a plane of symmetry here and then give me the boundary conditions as you model only half of this body, that there is certainly a tendency at this point up here to turn that into a pin joint instead of a welded joint by allowing rotations there, when in fact there are none for symmetric loading. If we assume this body is symmetrically loaded with the same loading on both sides, then there's no angular change there in the same way as for a welded joint. That's a symmetry condition, but is another example that I consider a little tougher. We also have considered in the past the concept of releases, and every commercial code allows this, typically at the end of a beam or at the end of a truss element. If you have a moment release, then that allows 2 beams that are joined together to move freely at the joint, and that becomes then a pivot point. Then, and would be characteristic of a pinned joint rather than a welded joint. Then you can also have a force release in which the 2 bodies are free to slide relative to each other, and that would be like a slot. And these are all built into the common commercial codes. We've considered 2 major categories of passive nodes in that last figure. One being the conventional welded type, and then the second being a released type of node, which is still passive. There are no active forces acting internal to that joint. Now let's go to a controlled node, which is more typical of robotics. Suppose you have a translational degree of freedom here at a common point to two different elements, and there's something in the nature of a rack and pinion gear. Then this particular little starred point here could be considered the node and could be considered controlling the displacement right and left of those members. It can put in a differential amount of translation there to actively control the displacement. Likewise, you could actively control the angular rotation between two members that might start off as shown in this figure over here, and then there might be some kind of a gear there that could make these two members move at angles relative to each other. Now, both cases of these involve some kind of force or moment being transmitted, typically equal and opposite to those two connected members. Here below, I'm saying that these active nodes can be modeled by this cloud-like structure here that will relate these degrees of freedom, J and K, let's say. We have to develop what that kind of a model would be. On the right, we have a similar model that might be controlling both translations and rotations. For infinitesimal translations and rotations, this is relatively easy to do. If you start getting into large displacements, this would get tougher. Notice that the translations might even be affected by the initial angle at which these are joined. We're going to concentrate in this lecture just on initially aligned bodies that are initially at the acting along the same line in translation, or in this latter case they will initially be aligned so that the angle starts out as a zero angle. Let's consider an actuator that is sensitive to position. We'll assume there's an actuator acting between these degrees of freedom, U2 and U3. The actuator will be trying to maintain a command gap here, defined as U3 minus U2. If we start both of those U3 and U2 variables as measured from the same starting point here, then you will have this as a true physical gap that should be maintained at some command value. If the gap gets larger than that value, then the actuator tries to close it with a force that's proportional, in this case, with a constant K, to the gap that actually occurs in excess of the command. The force F3 has a sign convention to the right in this figure, and so when we say there's a negative value here, we mean that it actually will act to the left when the gap is larger than desired. And see, that makes sense because it's trying to pull it back. The force F2 acts on the degree of freedom U2, and it likewise will try to pull to the right when the gap is larger than the command gap. Let's see if we can develop a mathematical model for this active joint. This is a new endeavor, and we don't know how it will turn out at the outset. But it will resolve into a kind of an artificial element that represents the actuator forces and displacements. Here's an exploded diagram above showing the independent coordinates. Then we show the equations that apply. There are 4 equations. We don't show the actuator forces yet. But we have given a formula for those actuator forces. If we treat them as if they are external forces F2 and F3 in these locations, then we introduce them below here. We're not putting in any true external forces at this stage. These equations are now coupled through the external forces, the quote external forces here, because they are functions, linear functions of the degrees of freedom 3 and 2. So in the next figure, we will move those terms to the left and incorporate those with the effective stiffness of the system. When I move those live loads from the right side to the left side, then we have what I call the standard form. And we see that the actuator stiffness K appears in 4 places in a symmetric form. Later, when we ponder over this, we'll realize that this is what's called a co-located actuator that senses a displacement and then applies forces at the same degrees of freedom. So if we think of the actuator as those terms with the K's, then we can separate out what appears to be an actuator finite element joining those 2 nodes as shown below. We'll put the command quantities within that small element model. So we have both the internal forces and these command forces all appearing as a part of this artificial element. Before using our new finite element model for an actuator, let's refine the model and bring in rate sensitivity as well as displacement sensitivity. Suppose we have a new cloud here hovering over these 2 nodes, and suppose this time the forces not only attempt to close a gap that is larger than desired, but also try to prevent a velocity of the gap larger than desired. Here is the measured gap velocity difference, saying whether or not the gap is opening up at a certain rate that's desired, and here is the desired value or the command value. The constant of proportionality here will be given a notation of C. You might think of it as damping in nature, but really it's a more general situation we might call a velocity-dependent force. So I'll use the symbol C. The force on the second node will tend to pull to the right when the gap is opening up too much. The force on the third node will tend to pull back to the left when the gap is opening up too much, or when the rate of opening is too much. Now we're ready to look at the equations of motion of those 2 line elements with the actuator between them. I've got the mass terms here, the damping type terms here, and the stiffness type terms here, and then the command forces over here. I'm using a tilde to distinguish the right element from the left element in all cases. The actuator puts in velocity-dependent terms that are shown here as these C terms. It puts in position-dependent terms that are given as these K's. And then these command forces are over here on the right. Our job is to separate out of these various terms which ones are due to the actuator so that we can identify now a set of equations that typify the actuator dynamics. I'll gather those terms in this figure. Here we have these terms that depend on the measured values of velocity and displacement. And then we have these desired values over here, the command values. So we now have, effectively, a line element on the left, and we know what its equation of motion is from earlier work. A line element on the right, and we know its equation of motion from earlier work. And then the actuator contribution from this work shown above. I ought to make some comments on this. Let's talk about the stability of such an active system. Notice that the damping and stiffness matrix quantities shown above are symmetric. There are no dynamic instabilities in this problem then due to the so-called coupled mode flutter, which requires non-symmetry in some of these terms. However, what you can get is a negative damping type of flutter where if this velocity-dependent force here had negative damping, then it could excite a fluttering motion, which is more typically a single degree of freedom type of flutter. So you want to watch that. Some people would call that a positive feedback, such as the screech in a amplifier at a public performance, where you get feedback between the loudspeaker and the microphone that the speaker wears. This is called a co-located model for the actuator, where it senses the motion at a point and applies the corrective forces at that same point. If you have non-co-located actuators and sensors, then you can apply the force at a different degree of freedom than sensed, and that can give circulatory effects or flutter, multi-degree of freedom flutter. The XY plotter, which has its gain turned up too much, and then you get an instability in the plotting pen, is an example of the single degree of freedom flutter, and you get positive feedback. An example of multiple degree of freedom flutter would be an example that I was told at Bendix Systems years ago about a large milling machine that had a bed on it that was controlled by two separate positioning devices on the right and the left. And both of these were given some gain on their control feedback. They were not interconnected electrically, but they were mechanically, in the sense that when one of these sensors sensed where the track was, it was affected by the flexibility in the system and where the other track was and what it was doing, and these two sensors started fighting each other, and apparently the forces became so great that this bed jumped right off of the milling machine on the floor, and the bed was an enormous one. It weighed a lot, something like half a ton or something, and so this was rather dismaying at that time, and you can bet that they fixed that pretty quickly. Well, we need to have an example now of this sort of a robotic situation. I'm going to choose a mechanical Flyswatter, which is an arm-like body with a rotational joint. So we'll consider just one active node here at the joint and one elastic beam here. The arm at the left I'll consider rigid, and for simplicity I won't even give degrees of freedom at the wall, but we'll characterize that rigid stub just with 2 degrees of freedom here at the joint. Now the elastic body has to be given degrees of freedom at both the joint and the free tip. I'll show those in the next figure. Our motion is going to be constrained to lie in the XY plane, and I'm going to neglect structural damping in this structural assembly. Now the idea is for this arm to reach up and swat a fly, so it has the ability to move through a rotary motion here. Now for small deflection theory of the Euler-Bernoulli beam, you actually are constrained that tip degree of freedom will move vertically, and then the rotations take place about the initial flat position. So we'll use a rotary actuator to control the degrees of freedom 2 and 4 that are shown in the figure. Degrees of freedom U1 and U3 will be pinned so that they are constrained to not be different. And ultimately, U1 is held in space because the shoulder of this device is rigid. But U2 and U4 can take different values because that's the active joint with the moment between them being controlled by an actuator. The tip has these 2 degrees of freedom. Alright, so our actuator here will be characterized by this moment acting on degree of freedom 4. When the angles are greater than the command difference in angle, then the moment wants to bring this body back again and will put a moment in this direction, which is negative in our sign convention. Notice that the sign convention shown here is for a right-handed coordinate system in which Z is coming out of the plane of the paper toward the viewer. Therefore, you get these counterclockwise displacements as the positive sign sense. And then this force here tends to oppose the arm when it tries to rotate more than it should. F2, as previously, is a moment acting on the stub, this rigid stub, and acts in the opposite sense as F4. The arms initially at rest at time 0 and is initially flat across here. And the fly is given a position where it has a little head start of a unit value plus the sine of 20t. I've chosen this to be an oscillatory fly path, so the fly is going to be moving up and down here at a given location on the wall. So its motion is characterized completely by this coordinate U7. The geometry of this system is very interesting, and we'll carefully lay out the angles that we're measuring in this figure. First of all, the position of the fly is an absolute known, and it's exactly known. That angle will be the position of the fly relative to this point over here, and we can measure that angle U7 exactly. Now the actuator and the sensor that goes with it are measuring this angle of the base of the elastic beam and using U4 here to characterize that left slope of the beam. Now unfortunately, rather than extending out straight as our formula is predicting, the actual beam has elastic motion that might carry it somewhere else and might even lie on the other side of the command position. So it is possible that you could get this actuator system providing at an instant of time a moment that is going in the wrong direction. For instance, in this current figure, the restoring moment would be trying to push the tip of the beam down by putting a clockwise rotation at the left here. The tip of the beam is already too low, and so at least at that instant of time, it would appear that's in the, quote, wrong direction. And then you have to see how that works out as time marches on. So the control system does not explicitly consider what the elastic deformation is doing. We want this co-located approach. And we'd have to say that the control is degraded by the presence of that elasticity. Let me tell you the physical properties of our system now, and I've had to scale the flexibility of the rod and the stiffness and damping in the actuator to make a decent dynamics problem. I'll use English units. 1/8 inch diameter steel rod is the Flyswatter, 30 inches long with the material properties for steel. These are the actuator stiffness and damping coefficients. The units on the rotational damping might look a little strange at first, and remember this is a moment per angular rate here. We're going to let the fly start with a head start. It starts with 1 plus sine of 20t. So if I were to plot its position, vertical position, as a function of time out here, I would have a curve something like this in time. Now this fly might be considered suicidal because it starts going away from the rod that is going to start chasing it, and then at some point turns around and comes back. But I needed just to pick some candidate motion. We'll set up the equations of motion for this system. We'll start by looking at the stiffnesses of the Flyswatter arm and the rigid stub. The rigid stub, when you reduce the degrees of freedom to the 5, not including U3, which we'll eliminate by setting it equal to U1, gives us this form. So our rigid wall has these 4 infinities over here. The beam stiffness, using Euler-Bernoulli beam theory, connects the 4 degrees of freedom then. It would be 1, 4, 5, and 6 in the reduced set. Here's the actuator stiffness, connecting degrees of freedom 2 and 4. And then here's the sum of all the system stiffnesses. Next we add the damping in the system. These are really actuator velocity dependent forces. Then we have the inertia here, which is the just the material mass of the Flyswatter rod itself. I'm currently carrying 5 independent degrees of freedom. Let's reduce that down to the 3 that are not constrained. The rigid stub at the wall effectively constrains degrees of freedom 1 and 2, so let's remove those. Now we have the system described in terms of the truly flexible degrees of freedom 4, 5, and 6 that remain. On the right we have the command values for the actuator moment, and we know that the fly position is given by the angle that the fly makes, so that you have to divide its translational distance by the distance out from the pivot point. Let's now numerically integrate the equation of motion. We previously made a homemade Fortran program called FEMNU to do such an integration. It has some specific problem-dependent sections like the main program and the force program that depend on the application at hand. So we need a new main program to define the physical constants in this Flyswatter problem, and we need a force subroutine to bring in those command moments dependent on the path of the fly. We'd like to know when the rod hits the fly, and it's more like a mush because they hit at this vertical intersection point right at a wall, let's say, that the fly is crawling on. To get an accurate time there, would be wise to take a very short integrating time step and maybe integrate only over the first 0.2 of a second. I would call that short time behavior. But I also am wondering how this Flyswatter behaves for a long time. If it passes the fly and doesn't kill it, then how does it track the fly over long periods of time? This sort of a chase problem is also similar to what might be used in a military situation with one fighter aircraft chasing another. And you would like to know what would happen if you didn't score a hit on your first burst of fire. What happens after that? Do you perhaps crash into the other airplane, or it catches you, or some unfavorable thing with long time? The integration works well, and we get these results. We're plotting here the motion of the tip of the elastic Flyswatter at the wall that the fly is crawling on. And interestingly, after a short time, we find the tip actually moves downward, That's due to the elastic mode of vibration of the flexible rod. Then, however, as it is pressed into action and made to go after the fly, it has this slight oscillating motion imposed on a more general motion, and it crosses the fly's path at 0.81 seconds. It then flies past the fly, realizes it's too far, tries to come back, and then ultimately will intersect multiple times with the fly's path. What you really have then is a form of desired rigid body motion of the Flyswatter arm that the actuator is attempting to impose, but then the actuator has its own elastic motion on top of that. And so this wiggling you're seeing is definitely a first elastic mode response of the rod itself. The long-time solution is important because we want to have a general idea of how the aiming mechanism that we've described here tracks the fly's motion. There are some cases where you'd like to accurately point at the fly only once. Other times you might want to track that fly, as in the case of a chase between two fighter airplanes. There is a joke, you know, about which clock is more accurate, one that's stopped or one that is running 5 minutes fast during a day. And of course, if you were judging by when a clock is exactly accurate, the one that's a little bit fast is worse than the one that is stopped, because the stop clock is at least correct twice a day. In our case, so we want to look a little bit at stability of this system and see if our tracking mechanism does something crazy as time goes on. This figure shows the repeat of the phenomenon that we saw at first, namely that the tip of the Flyswatter goes negative at the outset, which is in the wrong direction, you might say. You can see the elastic mode superposed on top of the more of the dominant motion, and is which the tracking of the control system is attempting to follow the fly. So the frequency of these larger sine-like waves would be governed by the fly's frequency pretty much. Now notice that we do overshoot after smushing the fly the first time. We come back, hit it again, and so on. There's an envelope here of motion then according to the Flyswatter's control system, which is like such, and then you have the higher frequency of that arm motion that governed more by the fly's motion. Sometimes this is called a beating mechanism. It'd be interesting to carry this on farther, even to longer times, and see whether that settles into some stable pattern. I'll leave that as an assignment for some of the more aggressive viewers in the lecture series. Years ago, I used to give this robotic Flyswatter problem to my dynamics class in finite elements at the University of Michigan. And I usually assigned it as a Newmark integration program to be done by a homemade program in Fortran by the students. One year, one of the students said, "Professor Anderson, I think you can do this with MSc NASTRAN." And of course you can. I realized that it might be a little tricky, but try it. And the student couldn't do it that year. The next year I gave the students the option of doing either a homemade program solution or a NASTRAN solution. And one of the students completely finished the problem, which I thought was very good. I'll run through my version of this solution using MSc NASTRAN. And there's a couple tricks involved. The simplest solution uses one bar element shown here, and then a damping element, CDAMP2, that provides the velocity dependent force that connects the rotations at these two nodes. And then I use two concentrated spring elements, CELAS2, one for the stiffness of the actuator, and the other is in an artificial solution out here for the position of the fly. It's very difficult in most commercial codes to enforce time-dependent displacements, and that's often done with an artifice. You can do it with a large mass, or in this case a large spring, where I put a force over a known force over a known large spring, and then this node here pops immediately to the static result. Now that's a massless grid point, and NASTRAN can handle that. Some other codes might have trouble with that, depending on the code. This worked well, and I'll show you the commands for the NASTRAN data set, and then I'll show the results. Let's take a look at the executive control and the case control commands in this figure. Here I have the two 8-character words that are on my ID card. We'll estimate 2-minute run time. SOL 109 is the direct transient response. I have the echoed data in the sort form, a title and a subtitle to be used on labeling figures and tabular output. I ask for all the displacements to be printed out. Those will be our plotting information. The dynamic load card here sets up the loads, both the artificial load on the fly position to create the position of the fly, and then the dynamic loads that result from the control system. And those would be the command loads appearing on the right side of the equation. Our time steps are chosen here, and depending whether we want a short time or a long time solution, we pick those steps. The plotting package here is set up within NASTRAN to plot the position of the fly and the tip of the Flyswatter arm to see when the intersection occurs. In the bulk data, we have to give enough information to define the geometry of the problem, the loads, and I'm adding this new condition that we're going to have the position of the fly, which I'm not interested mechanically, I'm just interested in getting a plot so I can add the fly's position to the plot of the mechanical response.